So continuing from the previous video, so we can input these values over here. So now a will become 0 because we are talking in terms of u. So because for t is equal to a, in this case u will be 0, so 0, and then for t is equal to infinity, u will be also infinity, and this will be e power minus s, and t will be given as a plus u, and then g will be now a plus u, okay, and then it will be du. So now we further decompose it, so it will be a e power a minus as. So e power minus as can be taken out, so e power minus as into 0 infinity, that will be e power minus us or su, okay, su, and then g a plus u du. So now we can see that this is the form of the Laplace transform, okay, this is the Laplace transform, a plus u, okay. This is the Laplace transform. So what Laplace transform is this? A e power a minus as into Laplace of g a plus t, okay, because we are talking taking a Laplace transform in terms of the u, so, and then its original function was in t, so it is a Laplace transform of g into a plus t. So it means that if we have a function in t and then times multiplied by the unit step function, so it's a Laplace we can now easily determine by taking the Laplace of that function by replacing the value of t by a plus t. So there is no need to convert it into t minus a format, so which will be a little bit tedious. So we can see this with the help of one example. Okay, so suppose that we can apply both approaches. Okay, so suppose that we want to find the Laplace of cosine of t u t minus pi. Okay, so in the original approach, so we have to convert this t into cosine of t into t minus pi. So we will write it like cosine of t minus pi, okay, and then u t minus pi. But in this case, it has to be equivalent to this cosine of t. So we'd have to do some. I have to do some manipulations. Okay. So what is cosine of t minus pi? So whether it is equal to cosine of t, so or not. So we need to find. So so I can determine what is cosine of t minus pi. Cosine of t minus pi is in whether it is equivalent to some other function. So for example, what is cosine of t minus pi? Okay, I can write it cosine of t minus pi is cosine of t cosine of pi plus sine of t sine of pi. Okay, maybe we don't need a triangle over here. So it is actually now cosine of t cosine of pi, so it is -1 minus cosine of t minus cosine of t, and then this term is 0, so the second term is 0. So actually when we write it like this, cosine of t minus pi, it is actually minus cosine of t. So I have to write minus over here, so then that it is equivalent to its original term. So now I can apply that this one, for example, Laplace inverse of e power minus as fs, okay, is equal to f of t minus a into sorry, we are not taking the Laplace, we are taking the Laplace. So for example, now this t shifting theorem is, for example, Laplace of f of t minus a into u of t minus a is equal to e power minus as f of s. So now we have it in this form. So then we can write it that because f of s, so f of s is corresponding to cosine of t. Okay, so we can write it like e power minus as, and then for cosine of t it is it will be s over s square plus 1, s square plus 1. Okay, and then it will be, there will be a negative sign over here. So in this way this approach will work. However, in this in the second approach, like this, which we have found over here, Laplace of cosine of t u of t minus pi. So we can directly write the Laplace. So for example, in this case, this is the function gt, and this is the unit step function with a value of a is equal to pi. So we can write it like e power minus pi s. Yeah, here it should be also, we can replace a with pi. So here in the second approach, so according to this formula, so it will be e power minus pi s, and then it will be the Laplace of cosine a plus t. So it will be t plus pi. Okay, Laplace of cosine t plus pi. So we can simplify it, cosine t plus pi, as that will be equal to cosine of t cosine of pi minus sine of t sine of pi. So it will be minus cosine of t, okay, because cosine of pi is minus 1. So it will be actually minus e power minus pi s Laplace of cosine of t. So now we know that Laplace of cosine of t is s over s square plus 1. So in this case, in the second approach, we don't have to do much mental exercise for converting cosine of t into cosine of t minus pi, and then making sure that its form is equivalent to the original function. In the second approach, which we have just in this case, when we have used this formula, it is much more direct. Okay, so so the second approach gives a much more direct application of this, and then it makes it easy to find the Laplace transform. So next we will see one initial value problem using the unit step function. Okay, so the initial value problem is this y prime. It is the first order equation, y prime plus y is equal to some function of t, okay, where this function of t is a piecewise defined function. So y0 is equal to 5. So how this function is defined? This function is defined as this, like this. It is 0 for values of 0 for values of t from t to pi, and it is equal to 3 cosine of t from values of t greater than pi. So in this way, then we can write this function in the unit step format as 3 cosine of t into ut minus pi. So we can verify it. So for example, if the value of t is less than pi, so this will be 0. So f of t will be 0. That is okay. And if the value of t is greater than pi, if this u function will be 1, so it will be 3 of cosine t. So this is the correct representation. So for this, the Laplace transform will be of this function will be, because we need the Laplace transform when we are going to take the Laplace transform of this equation. So the Laplace transform of this will be equal to 3 times. We can now apply this formula, Laplace of g of t into u t minus a is equal to the e power minus as, then the Laplace of g of t plus a. So this is the simplified formula we can apply. So it will be e power minus as. As will be, in this case, pi. A will be pi. In this case is pi. So e power minus pi s. And Laplace of cosine t plus pi. So cosine t plus pi is minus cosine t. So t is equal to e power minus pi s. It is the Laplace of minus cosine t. It will be minus cosine t, and the this minus sign will go out, so it will be minus 3s over s square plus 1. So this will be the and then of course e power minus pi s is here, e power pi s in s over s square plus 1. So this will be the Laplace transform of this function. So now we take the Laplace transform of this differential equation. So y prime Laplace is s capital Y and minus y of 0, and then for y it is capital Y, and for f of s we have already found this Laplace transform, 3 s over s square plus 1 e power minus pi s. So we take s plus 1 as common out of y, and then this should be minus, so it is minus 5. Y0 was 5, so it will be 5, and then it is minus 3s over s square plus 1 into e power minus pi s. Here what we can do is, now we can write it in terms of y. So we take 5 on the other side and then divide by s plus 1, and now for this we take 3, okay, and then we take this term s plus 1 into s square plus 1 in the bracket e power minus pi s. So we can write it like this, okay. You should all agree that we can write it like this. So but in this term now we have to take the inverse Laplace transform. So the inverse Laplace transform for 5 over s plus 1 is easy, so we can apply this formula. Laplace of e power at is equal to 1 over s minus a. So it will be e power minus at. But for this we need to use the partial fractions to convert it into some reasonable fractions, which we can easily take the inverse. Okay, so s over s plus 1 into s square plus 1. So we can take the partial fractions, and then for this type of format we assume a over s plus 1, and since this is s square plus 1 cannot be factorized, so for this we need to take this type of term, bs plus c over s square plus 1. So there will be 3 unknowns over here. So now we can write it like this by multiplying by s and s plus 1 and s square plus 1. So we can write it like this: a into s square plus 1 plus bs plus c into s plus 1. Okay, so we will continue this in the next video clip.